angle lens has a short focal length, and you can use that to capture objects that are close, and a telephoto lens that has much longer focal length for distant objects, right? So we talked about the lens, but we really didn't talk about this thing behind the lens that is very, very important. It's an aperture, right? So what the aperture does is it decides how much light that is collected by the lens is actually going to go into the camera, right? So you can have apertures of different sizes like you see here. So if the aperture is completely open, all the light goes in. If the aperture is only a little open, then only a little light goes in, right? So now based on this, we can think about it more scientifically, right? So we'll define a term, right, that you know already probably as irradiance. Irradiance is power per unit area. Power is watts, right, per meter square. How much light power per unit area is falling beyond the aperture, right? That is what we are calling irradiance, and its units are watt per meter square. But watt is a joule per second, so I can also write this as joule per second meter square, right? So bear this in mind. We'll come back to this, okay? Joule per meter second meter square is the irradiance. We denote this irradiance as E. Okay. So now, if I have an aperture of diameter d, then the light that is going through this aperture is obviously proportional to the area of this aperture. If it is wider, then more light goes in. If it's narrower, less light goes in. So irradiance E is proportional to the area of the aperture. So we write a d square, and it is inversely proportional to the area of the image. And so we have d square here, that is the area of the image, right? And then we know also from our when we studied lenses that magnification, that is height of the image by height of the object, could be expressed in terms of object and image distances. So using that, I'm not going to go into the math of that. Using that, you can extend this irradiance to look like d by f square, where f is the focal length of the lens and d is the size of the aperture. Now we can define a new term, that is f by d, that is the focal length of the lens divided by the diameter of the aperture, as the f number. So this is called the f number, and it's often denoted as a. But unfortunately, many times what you are given for f number is not f over d, you are rather given f over a. So if you look at a lens that gives you something like f over 8, right? This 8 has nothing to do with the diameter of the aperture. So in the if you buy a commercial camera or commercial lens, it has an f number of f over 8. This denominator 8 has nothing to do with the diameter, really, because in commercial cameras, what they're giving you as f number is actually the focal length divided by this a, which is the a itself, right? So in that sense, in that sense, this 8 is essentially the diameter. They're not giving you f by d, but they're giving you f by a when you look at a commercial f number, right? So now if I define a as f over d, I can rewrite the irradiance in terms of a as 1 over a square, right? So why are we doing all this? Because when you're doing when you're trying to capture images, you can use different lenses with different f numbers and different exposure times. Where did this exposure time come from? Ultimately, what you want is you want to capture certain energy of light onto your film, right? So you want to let in certain energy into the camera. So when the aperture is open to a certain extent, it lets in a certain amount of power, right? The duration for which it is open decides how much energy would enter the camera, right? So the total energy would be how much irradiance you have multiplied by the exposure time, right? So the total energy that you have would be irradiance, right? The irradiance, recall I told you, is in the units of joule, meters, joule per second. Joule per second is what? Meter square, right? So you have to multiply this with second, or you have to multiply it with time, t, to get rid of the seconds in the denominator and get joule per meter square, which is energy, right? So now that we know how these f numbers work, you can see that, for example, if you have a lens of, let's say, you have a commercial lens that has f by 8, right? F number, right? And you are given an exposure time of 150, 1 by 50 seconds. Okay. So if I have to double the exposure time, what should be the f number that I should choose, right? I got a very good image using f over 8. I got a very good image using f over 8. I got a very good image using f over 8. F over 8 and an exposure time of 1 over 50 seconds. Now I want to double the exposure time. So if I double the exposure time to 1 over 100 seconds, what would be the necessary f number? So you can do that very easily. You know that f number, for example, if you have f by 8, this number 8 you know is really a, right? Is really a, letter A. So then I can write, in case of f over 8 lens, in case of f over 8 lens, this 8 is the A, right? So energy, so the energy would be equal to 1 over 8 square, or 1 over 64, and exposure time we said was 1 over 50 seconds. So the total energy then, this is not irradiance anymore, I'm writing total energy, is the irradiance, which is 1 over a square, 1 over 64 divided by 1 by 50 seconds. See where we are getting this from, right? We were given an f number of f over 8, and this denominator 8 is really the number a. So you can get the irradiance by doing inverse square. So that's how we got 1 over 64. And then the exposure time is 1 over 50, right? So now if I want to double the exposure time, what should be my best suited f number, right? So I can write that as 1 over x here, right? And equate these two, right? then if I do that, um, so 50 goes into the numerator, so 50 crosses off 2, right? uh, 2 goes there, 2 crosses of this, that would give you 32. So x is equal to 32, but recall that we have to square it here, so we have to take square root of 32. So take square root of 32, square root of 32, square root of 36 is 6, square root of 5 is 25, 25, 36, ballpark 5.6, right? This is what you're supposed to do as a physicist, right? We're not engineers, right? 5.6. So if I want to double the exposure time, I would need to use an F number of F by 5.6, right? If I had an F by 8 lens, which I used with an exposure time of 1 over 50 seconds to get a good image, okay, but now I need to increase the exposure time, right, because I would like to capture something longer for 1 over 100 seconds, then I need to change my F number. I cannot just simply double the exposure time with the same F number. You would not get the same exposure. If you want to get the same exposure, you have to change the F number, right? So that's why this math gives you a useful way to look at things. So now here you can see the F number in action. So as the F number changes, as the aperture increases, right, the exposure time decreases. As the aperture decreases up here, the exposure time increases. So that for all these three combination, right, you would have basically the same or similar exposure, right? Because higher time, longer time compensates for smaller aperture opening, right? Okay, so the combination of shutter speed and the aperture is not always arbitrary, right? And the shutter speed must be fast, because if you have moving objects, for example, let's say you're trying to capture the image of a cheetah or a puma that's running in the wild, right? You have to keep up with that and not blur the image, right? So these are very, very important, right? So so to look at that, we look at something called the depth of field. What the depth of field means is, for example, if I have an object at O, right? I have an object at O, and this arrow here indicates my camera. This is my camera system. So light rays from my object O are going into the camera, and then they converge upon the film at O prime here, okay, at O prime, right? But it's not just the rays from object O, right? There could be rays from another point here N, or another point here M, that could also converge to different points, like here M prime or N prime, and they would also appear in the picture, making the picture blurred. So this length Mn is called the depth of field. So if you want to get a sharp image, you want to reduce the depth of field. So you want to change the lens and exposure combinations to change depth of field. To change the depth of field, and so this D, little d you see here, is called a circle of confusion. Circle of confusion, because here what you're looking at is a 2D picture, but in reality all the light rays are going in 3D. So if you were to look at it from here, right, if you were to look at it from this point, right, then this in 3D this appears like a circle, right? This is a cone of light actually. So the cross section of a cone of light is a circle, and the diameter of that circle is d, right? When that is minimized, you have good depth of field, that is called the circle of least confusion. Okay. Now, obviously, so far here we just talked about lens, okay, but we really have not talked about aberrations that come from lens. Um, we talked about polychromatic aberrations, for example, because the refractive index of a lens is not the same for each wavelength of light. Different wavelengths of light, as we have seen while studying the achromatic doublet, is different for different wavelengths. So to account for that, sometimes you have to have achromatic doublets in your system, or sometimes you may need to have a negative meniscus lens. So depending upon the system, to collect more light, you may need to have a larger numerical aperture. So designing this lens itself is an art, right? And so these are different types of lenses. So we discussed this particular combination before. We discussed this achromatic double meniscus. This basically removes polychromatic aberration. That is, the refractive index for blue and red is different, right? So the refractive index for blue is lower. Sorry, the blue refractive index for blue is higher, and refractive index for red is lower. So red goes farther than blue. So you would have a blurred image. But if you put an achromatic doublet, they sort of cancel each other and bring red and blue back. If you haven't watched the achromatic doublet example video, please go back and watch that. So that's what it is doing. So even this is an achromatic doublet. So or even this is an achromatic doublet. So these kind of things are put into the lenses. The lens design is a little more complicated in the camera in order to get rid of aberrations, in order to get rid of chromatic aberrations, spherical aberrations, so on and so forth, right? Now let's look at something else interesting. So this is your traditional camera, right? A DSLR point and shoot camera, right? So uh, uh, if you close the cap, right, there is still light. You cannot have darkness. What is darkness? Right? This is a more of a philosophical question. What is darkness? Can there be no light? Can there be nothing? Right? Nothing by definition is not existent. Right? How can nothing be existent? Right? Nothing is not anything. Nothing is not existent. So pure darkness is not existent. So ideally, if the camera cap is closed, you should see a dark image like this. But this is not what you would see. You would see something like this, even at a low temperature like minus 21 degrees C. That is because you have these 0 point fluctuations in the quantum field from atoms moving around. We need to do a little more of quantum electrodynamics to see why this comes about. But here, from a technological aspect, you do get these background images, right? And so you have to get rid of these. So nowadays you have all the software and everything integrated into the camera. If not, you could do it on the laptops or different softwares to get rid of the background images. But the background images come from basically the 0 point motion of the electrons or atoms. The molecules are not ever at rest. They're constantly vibrating, and so because they're constantly vibrating, you would get these pictures like this, right? So I think with that we will stop our lecture on camera, and in the next lecture we'll talk about wave optics. Thank you.